Dear friends, hearty welcome to the online problem solving session on group theory organized by Maths Aspirants. As you may know, Maths Aspirants is a collective of mathematics students, research scholars, postdoc fellows, faculty members across India and abroad, initiated by myself in 2017. And we used to organize several online programs to help the students who pursue higher mathematics. As a part of the online problem solving session series, today we're blessed to have Ms. Ekta Seth with us to handle a problem solving session, actually a series of problem solving sessions on group theory. Ms. Ekta is from Uttar Pradesh and she did her master's from Banaras Hindu University and now pursuing PhD at Hyderabad Central University, and her broad research area is abstract algebra. She qualified CSIR NET, GATE and other exams, and I am sure that today's session on group theory, she will explain the basics and also discuss some previous year questions that will certainly help you in your preparations. And also, she agreed to take more sessions on group theory to cover the syllabus topics from the syllabus of IIT JAM as well as CSIR NET. I'm sure that today's session will be really beneficial to all those who are seriously preparing for these exams. I welcome everyone to this program, and I would like to express my thanks to Ekta for being with Math Aspirants and for joining this session. I extend my warm welcome to Ms. Ekta. Thank you.
Good morning, everyone. First, I would like to say thank you to Vinod sir for giving me this opportunity. Okay, so here is the syllabus of abstract algebra for IIT JAM. So what I did, I divided it into subsections. So in today's session, what we will do for basics definition like group and a subgroup, abelian group, non-abelian group. We will see some examples and we will see some previous year question papers. Okay. So here is the mark distribution. So for IIT JAM, they will ask like 10 to 13 marks. So this is about 10% of whole marks. And for CSIR NET GRF, they will ask like 25 to 45 marks. But in CSIR NET GRF, we have ring theory, some field extension and all. And similarly in GATE syllabus is little bit more. But for IIT JAM, we have abstract algebra only. Okay, so we will start from basics. First of all, binary operation. To define a group, first we need an operation and not any operation. We need a binary operation. Binary operation is nothing but like a closure property. Let G be any non-empty set. A function start from G cross G to Z is called a binary operation in C. And second, we will define commutative binary operation. Star is said to be a commutative if A star B is equal to B star A for all AB belongs to G. Okay, here are some few examples of binary operations. Suppose our set G is equal to 1 and minus 1, then addition is not a binary operation on G. Because if we add 1 and minus 1, it will come 0 and 0 is not belonging to G. Similarly, we will take G is equal to integers. We know that if we add two integers, anyway it will come integers only, and A plus B is always equal to B plus A. So this is a commutative binary operation on Z. After this, we will go on a bigger set like a rational number. So what it will be with respect to addition? Can anyone give the answer of this?
Binary operation.
Okay. And what?
Binary operation.
Yeah. So means our rational number with respect to here in case of rational number, addition and multiplication is a binary operation. What about Q complement like set of irrational number? Is addition is making binary operation?
No.
Okay. Why?
Root 2 plus root 2 minus root 2 is equal to 0.
Yeah, correct. And what about this multiplication?
That is also not binary operation.
Why?
Again, root 2 times root 2 is 2, which is rational.
Yeah, correct. So after this, we will go to real number. Similarly, real number for real number addition and multiplication. This is a binary operation for this. After this, we will go to power set. Let X be any non-empty set, so power set of X. So what you people think with respect to union, intersection, and symmetric difference? It is a binary operation or not?
Union and
Binary
intersection
operation.
are binary operations. Symmetric
What?
union and intersection are binary operations.
What about symmetric difference?
And I think it is not.
Okay, what about others?
It is a binary operation.
Excuse me, symmetric difference is the union of difference of A minus B and B minus A.
Yeah. What do you think? It will form a binary operation or not?
Yeah, it is from binary operation.
Yes, ma'am. Binary
And
operation.
here each element of finite order.
Correct. Because symmetric difference is nothing but A minus B union B minus A. So A minus B is a set and B minus A is also a set. And if we will take a union of set, because power set is a set of all subsets of X. So it will come in Px only. So it will form a binary operation, with means this symmetric difference is a binary operation for Px. Okay. So here, if cardinality of G is equal to n, then number of binary operation on G is n to the power n square. Can anyone explain why it is happening? Means why number of binary operation on G is n to the power n square? Anyone guess? Okay. So here the thing
Binary
is, what we know if, yeah, number of binary operation on G. If cardinality of G is equal to A, then number of binary operation on G is n to the power n square. So can anyone explain this, why it is n to the power n square?
Binary operation is from G cross G to G. So cardinality of G cross G is n square. So number of binary operation will be n to the power n.
Yeah, so is it clear for you? Hello? Is it clear to everyone why it is n to the power n square?
Ma'am, is this the power set?
What?
Is this the power set?
What is the power set? What?
G.
Huh? Do you ask something related to power set? Hello?
Ekta, you can move on, no issue.
Okay, sir. So what we know, if we have a function from A to B and cardinality of A is suppose n and cardinality of B is m. So number of function from A to B is m to the power n. Here what we have, our function is binary operation we are defining from G cross G to G. So the cardinality of G cross G is n into n square, and cardinality of G is n itself. So number of binary operation will be equal to n to the power n square. And similarly, number of commutative binary operation on G is n to the power n plus 1 by 2. Since, because here what we are taking, like, since AB is equal to BA, means AB is equal to BA. So if we will see this in a matrix, so what we can do, it will look like a symmetric matrix. So, and what we know, the like in linear algebra, we know how to like dimension and all. So from there we will get n plus 1 by 2. Like it will be like first row, then second will start from A to 2, then third one start from A33 to A3n. Like that, if we will count, then we will get n plus 1 by 2. So it will be like n to the power n plus 1 by 2. So these are some examples. So number of binary operation on Z10 is, everyone is familiar with Z10, means Zn.
Ma'am, modulo 10, addition modulo 10.
What?
Addition modulo 10 on integer.
Here Z10 is 0 to 9. So can you say, means what will be the number of operations on Z10? Can
10 to the power 100.
10 to the power?
100.
Yeah, correct. So similarly, we can find the number of commutative binary operation on Z10. Okay, so here we will come to definition of group. Okay, so what is the group? Let G be a set, non-empty set together with a binary operation. So we say G is a group under the operation if it will satisfy the following condition. The first condition is associative. Usually in some book you will get the closure property, but here because we are taking binary operation, so no need to show closure property. So first property is star is associative. So what do we mean by associative? Means A star B star C should be equal to A star B star C. For all ABC belongs to Z. And second one is existence of identity. So there exists E belongs to Z such that A star E equal to E star A equal to E. So like we can think in real analysis. So means whenever we will add 0 to any real number, it will come to same number only. Is it?
Yes, ma'am.
0.
Yeah, so it is like same only. And if we will take like in multiplication, so if whenever we will multiply 1 to any number, it will come to same number. So this is the only identity. Same in group theory only. In different kind of structure, we have some elements such that if we will multiply or we will do some operation, it will come to same number. Oh, here I did some mistake, a typo here, error. It should be A star E equal to E star A equal to A not E. And like that. And second thing is existence of inverse. For each A belongs to G, there exists a B belongs to G such that A star B is equal to E. So this is our inverse function. So here are some basic example of group. Z plus, we know that addition is always associative, means from childhood we can see, we can add 2 plus 3 plus 4 in any way, it will come 9 only. So according to this, we can say it is associative. And what about identity? With respect to addition, we know that 0 is our identity. But what about inverse? What we will do for this, like A plus B equal to 0. So from here, what we will get, A equal to minus B. Means, A plus B equal to 0. So from here, we will get B equal to minus A. Means inverse of A is minus A with respect to addition. But if we will take Z with respect to multiplication, it will not form a group, because for 2, suppose 2 into B is equal to, 2 into B equal to 1. So we will get B equal to half, 1 by 2. But 1 by 2 is not an integer. So Z dot will not form a group. But with respect to rational, real, and complex, this will form group with respect to multiplication also. Here R star is denoting like means real number. Here we excluded 0 because we don't have any inverse of 0, because 1 by 0 it will form an infinity. So it is undefined. After this, we have this example 1 minus 1. I minus I is a group with complex multiplication. One can verify this. It is easy only. And after this, we have this set Z modulo n. So I think this is an exercise only, means one can see it's very basic concept in group theory. And I think so everyone is familiar with this. After this, we have one theorem. What is the theorem? Identity element of G is uniquely determined. Means in a group, we have a unique identity. We can't say we have a two different identity. And similarly, inverse of each element is uniquely determined. Since we don't have a time, so I am not going for proof and all, but here the hint is, if someone want to prove this, like for this, we can take two identity like E1 and E2. After that, what we can do, even into, since E1 is the identity and E2 is another identity, so E1 into E2 is equal to E, and E2 into E1 is equal to E2. So from here, by cancellation, we can see the result. And after this, we have a definition, abelian group. This is a very important definition in group theory. A group is abelian if A star B equal to B star A for all AB belongs to G. And what we will say non-abelian if G is not abelian. So suppose you have given a group, how will you prove it is a non-abelian group? So for this, what we need two elements such that A star B is not equal to B star A. So for this, we need a pair, just a pair A and B such that this condition is not satisfied. So here are some example of abelian group. So means this basic things are there like Z plus Q plus, a known number system only here we are taking, and all vector space are abelian groups. So if you people saw that definition of vector space, so from there to define a vector space, first we need an abelian group only. So with respect to plus, it is a abelian group. Okay. So here example of non-abelian group. So I think from class 11, 12, we are proving this, like showing this. I mean, suppose we have given two matrices A and B. So A into B need not be equal to B into A. So from there we can take an idea, means this is not a commutative. But the thing is, we want, here we are doing for group. So for group, what we need associative property, identity, inverse. For identity, we know that identity matrix is whenever we will multiply identity matrix to any matrix, it will come to same matrix only. So means this will form a general linear, means this set will form a group. Here we are taking determinant is not equal to 0, because whenever our determinant is 0, then we can't find inverse of a matrix. So we say this set general linear group. The general linear group is a group under usual matrix. What?
And what is Mn in general linear group?
What?
What is Mn in general linear group?
Mn in general linear group means this one, Mn over field F.
Yes.
Mn over F is a set of all matrices over F. Over F means their entries are means n cross n matrices, where elements are coming from F. Here F is a field.
Okay.
So GLN of F is a subset of Mn F. Means this is a n cross n matrix whose elements are coming from field F, but the thing is here determinant is not equal to 0. So we are taking element whose determinant is not equal to 0. We are taking that type of matrices only. Because if you will include matrix such that their determinant is 0, then we are not able to find out its inverse. But for group, we need inverse property also. Okay, so second one is special linear group SLN of F. So here what? Here we are taking this is a subset of GLN, because here determinant is equal to 1. So we are taking a specific matrix such that their determinant is coming 1. And this will also form a group under matrix multiplication. Here what we have, okay. So GLN is non-abelian whenever if and only if n is greater than equal to 2, and same thing is with SLN also. What about n equal to 1? If we will take n equal to 1 and a is not equal to 0, so it will give you entire field except 0. because 1 cross 1 matrix is nothing but that singleton element only. So, and in case of SL1, here we are taking all 1 cross 1 matrix such that their determinant is 1. So it will come 1 only, singleton 1 only. So here we will do some problem related to group. Okay. Okay, so this is the problem. Here VRG is the collection of all matrices such that their entries are same only. So what can we say about this? G plus is an abelian group. G with respect to multiplication is not a group. G cross is a group but need not be abelian. This is a typo error, it should be B. And G cross is abelian. So think about this. I am giving you 2 to 3 minutes to you people.
I think it is not be a group because inverse does not exist.
What?
It is not. I think it is not to be a group because
Huh.
inverse does not exist here. For how it is determinant will be equal to
Can you explain it again? I'm not able to hear you. Means what you said means it will not form a abelian group. Why? Something inverse like that you said.
yes, yes, and its determinant equal to 0. That is why.
No. Here we are taking A is not equal to 0 means like it's not about inverse. Means this G plus is not an abelian group, no? Here we are taking with respect to addition. Not with respect to multiplication. First one is with respect to addition.
Ma'am, it's not an abelian group because it's not a group first. As A is not equal to 0, we cannot have identity element under addition.
No, it's not like that. The first thing you should check whether it is a binary operation or not. Before going to group abelian group, first you people should check whether it is a binary operation or not. Is it a binary operation? First thing, is it a binary operation? First you people check, is it a binary operation or not?
It is not.
No, ma'am.
Why?
Because minus A, if A is not equal to 0, then minus A is not equal to 0. And if all the entries of the matrix are minus A, and I add A with minus A, then I get 0, which is not in the group.
Yeah, correct. What about the others? Everybody got it?
Yes, ma'am.
Okay. So what is the second? Means it is. What about these three options? Is it abelian group like that? Are you people trying? I want to get answer from others also. Don't be quiet. Okay, so I'm doing this.
Option C, ma'am. It
What?
is a group but need not be abelian. Group but need not be
Okay.
abelian.
Okay. What about others? There are 53 members, but no one is saying. Okay. So we will say the first thing is, suppose if here what we are taking, suppose we take a matrix A with all entries are equal to A, and for B we are taking like Bij such that all entries are equal to minus A. So whenever we add A plus B is what? Means Aij plus Bij. So it will means for a matrix we will do entry wise. So A minus A is equal to 0. So A plus B equal to 0. But here what is there in definition? A shouldn't be equal to 0. But here what we are getting? We are getting A plus B equal to 0 matrix. So it is not in our set, G set. So it will not, it is not a binary operation. So it will not form a group. And what about second option? Means we want to see it with respect to multiplication. So some people are saying like means all rows are same, so means 0 will come. Like it's not like that. Suppose our matrix A is looking like this and B is looking like this. If we will multiply this, so what we will get like A and AB and AB means all entries will come like an AB. Okay. So for identity, what we can do means for what is the identity? Suppose suppose B is any, suppose we are saying A is our identity and A is an element. So what we want A into E is equal to A. So if we will do like this, so here suppose B, I want to check, means I am saying B is my identity. So A into B should come equal to A. So NAB means this matrix should come equal to AAA. So if we will compare each entry of AB to be each entry of A, so what we will get NAB equal to A. So if we will cut that A, because here we are means it is coming in field, entries are coming from field. It is not equal to 0. So we cancel out A. So what we will get? NB equal to 1 means we will get B equal to 1 by N. So from here, our identity is 1 by N. Means all entries will be 1 by N. Is it clear to all of you?
Yes, ma'am.
What about
Yes,
others?
ma'am.
Yes, ma'am.
At least you can say in chat box, no? Okay. So this is the next we will try to find out inverse. What do we mean by inverse? Suppose if we have any matrix A, we want to find a matrix B such that AB should equal to E. So here what is our identity matrix? Our identity matrix is means a matrix such that its all entries are 1 by N. So if we will multiply A into B, here B is the inverse of A. From here what we can say, what we can see, AB is nothing but means a matrix such that all its entries are NAB. So we want to make it equal to E. So AB is equal to E. So what we will get, and this matrix AB, when we will equate this matrix AB equal to E. So means like this matrix, first one AB equal to E. After this, what we have to do? We have to compare each entries of AB with each entries of E. So we will get NAB equal to 1 by N. So here we want to find elements of B. Here, since each element is B, and from here what we are getting? From here we are getting B equal to 1 by B equal to 1 by AN square. So here our A inverse will be like a matrix such that all entries with 1 by AN square. Is it okay?
Yes, ma'am.
Yes, ma'am.
Yes,
Okay.
ma'am.
So what we got means like identity with identity and inverse. So is it associative? Matrix multiplication is associative, we know, and identity inverse. So means is it will form a group. Is it clear for clear to everyone?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So what secondly what we want to check, is it a Abelian group or not? Okay. So is it what? Since what we are getting in entries, AB equal to BA, You can check like by 3 cross 3 matrix or 2 cross 2 matrix. When you multiply, you will get like 2AB, 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 2AB. And for BA also, you people will get same only. Because here what we are doing, we are just we are multiplying like first row to first column. So anyway you will do, we are multiplying same element to means like suppose first we have taken AB. So here what we are doing, we are multiplying first column to first row. So like A to B. So it will come AB plus AB plus AB, and time it will come NAB, our first entry. Similarly, for BA, what we are doing, first we are taking matrix B, then we are taking matrix A. So for matrix B, what we are taking like B. So this means this row we are multiplying with first column of A. So anyway, it is coming BA plus BA, and times it will come like NBA. But this is here AB equal to BA because we are taking from real number only. So means like field only. So it will be same only. Okay. Is it clear to everyone why it is a abelian group? You can check
Yes,
for 2 cross 2 matrix or 3 cross 3 matrix. Okay. So after this, we have this Stokes and Sewell's theorem. If AB belongs to Z, then AB inverse will be equal to B inverse into A inverse. Okay. So after this, we will do some problem. Okay. This is the problem. Huh?
Ma'am, what is WOTF?
What? Which of the following? Which of the following is that true for a group G?
Okay, ma'am.
So here our first question is G is abelian if only if AB inverse equal to A inverse B inverse for all AB belongs to G. So I'm giving you time. Try to think about first question. After that, we will see a second one.
Ma'am, the first option and the third option are correct.
Okay.
Other
What
three
about
are false.
other three are false? Second one is false according to you?
Yes, ma'am. If we take matrix, and
What about others?
Second is also
first,
correct.
second.
Ah.
Ma'am, first, second, and third are correct.
And what about fourth and fifth one? If someone can't open means his or her mic, then they can message in chat box also. Now I will see from there.
One can take example like Heisenberg group.
For what?
Where the entries are from Z3. Yeah, that way one can construct like the diagonal element are 1, 1, 1, and in the upper diagonal are like ABC, where ABC are from Z3, and the
Yeah.
lower diagonal are 0, 0, 0. Yeah.
Yeah, correct. Okay, so we will see the solution. So for first one, what? AB inverse is equal to A inverse B inverse. So here we will take its inverse again. So according to Stokes and Sewell's theorem, what we can say, because inverse of A inverse is a same element only. So it will become AB, and for the second part, it will come second element B inverse of inverse, and then A inverse of inverse. So from here, what we will get AB equal to BA. So from here, we can say that G is an abelian. This is the first case. Second, what we are saying, G is abelian if only if AB square is equal to A square, B square. So how it is coming? So we have taken that right hand side AB square. Suppose AB square equal to A square B square. So this is AB square. So we can write it like AB into AB, and the second one AB, B. Since this is the group, so we have cancellation property. So from here, we can cancel by left cancellation, we can cancel A. From right, we can cancel B. So we will get BA equal to AB for all AB belongs to G. So G is an abelian group. Okay, so after this, we will check for third one. So according to, if A square equal to E, then what we can say A into A equal to E. So this means A inverse equal to A for all A belongs to G. So here AB inverse equal to B inverse A inverse. So it will imply, because every element is self inverse only. So AB inverse is nothing but AB only. So AB will equal to A inverse B inverse. But since again B and A is element of group G and it is a self inverse only, it has self inverse only, so it will be equal to B into A. So from here G is an abelian group only. Okay, so for fourth and fifth, I took some counter example. Someone I think said this example. So here my G is a collection of all matrices such that on diagonal we have one, and for others means this is the upper triangular matrix. For others we have ABC, and this ABC is coming from Z3. So here suppose A is equal to this and B is equal to this matrix. So if we will take A cube, it will come like this, because here this is a 3A1, 3B1, 3C1 and entities are coming from Z3 like modulo 3. So that's why it will make it 0. So we will get identity element only. Similarly, this is for B also. So if we will take B cube, then it will become identity only. So it is satisfying first condition, A cube and B cube equal to identity. But now we want to check whether A is it abelian or not. So what we check here, if we will multiply A to B, we will get this matrix, and if we will multiply B to A means BA, then we will get this. These two matrices are not equal, so we can say that it is not a abelian group. So where is the fifth question? Okay. So G is abelian if this. So this condition is not true because okay.
Excuse me. Fourth one, you are taking a counter example, okay? Okay. Fourth one is also not true.
For A cube, we take counter example. After then,
Ma'am, can you show the counter example?
okay, counter example. Okay, I will show.
It has gone above. Okay, thank you.
Your voice is not coming.
Ma'am, what is this group called?
Group actually one 𝕾𝕐𝕬𝕧 Hamiltonian group.
Sorry, ma'am, one time?
One 𝕾𝕬𝕧 Hamiltonian group like this.
Okay.
Everyone is getting this?
Ma'am, is there
Anyone
also
have doubt? What?
is there also Heisenberg group?
Sorry, Heisenberg group. I did mistake. I said what Hamiltonian group. Sorry. That is something like with the help of complex number we used to make. Sorry. This is Heisenberg group.
Ma'am, what is the difference between the two?
What?
What is the difference between the two?
Difference between what? These two groups?
Yes.
Actually, the thing is, we are defining our matrices. That is with the help of some complex thing is there, like Actually, I don't remember properly, but that is related, means their entries are coming from complex numbers and all, means like Hamiltonian group now. Like we have got Gradient group 1 minus 1. I
Maybe
need
some
to.
sort of polynomial in terms of I, J, and K, right?
Yeah, correct. Like that only.
And ma'am, Heisenberg group is upper triangular form.
Yeah. Shall I go ahead?
Yeah, ma'am.
Okay. So for a fifth, we will take same examples, because here AB is also belonging to G. So here its cube will be equal to identity. And A cube, B cube means A cube is identity, B cube is identity. So their product will be equal to identity only. But G is not a abelian group. So here is the third problem. If G is an abelian, then if A square equal to E for A belongs to Z, suppose if G is an abelian group, then it will imply A square equal to E for all A belongs to Z. And the second one, there exists A belongs to G such that A is not equal to E and B square equal to E. Is it true?
Yes, ma'am.
Uh, what about others?
What is your question, ma'am?
The question is, suppose you have given an abelian group, so what can you say? Means A square will be equal to E for all A belongs to Z.
This is not true.
Why?
Ma'am, take a cyclic.
What?
Z7. Z7.
So can you give some example in Z7?
Z7 take 6.
Okay. What about others? What about second part?
True.
This is not true also. If we take odd order, then then there does not exist any element such that A square.
Yeah. Okay. Anyone want to tell something about this problem? Okay, so I am going. So simply we can take the group Z equal to Z plus. Okay, so here, because here we are taking addition of any integer need not be equal to 0. Is it? And Z plus is an abelian group. Is it fine for everyone?
Yes, ma'am.
Huh? Okay, so similarly for second case also. Except 0, if we are taking like 1 plus 1 is not, 1 plus 1 is equal to 2. Anyway, it is not going to be 0. Okay. So after this, we have this question. I think this question is asked in IIT 2017. So I'm giving you few minutes. Just try it. Question is clear to everyone. Shall I?
Yeah. Yes.
Okay. Shall I move, or you people want to take some time? Everyone is getting question or not?
Yes, ma'am. Trying.
Okay, so I'm explaining this. Okay. So first, what it is, I think the binary operation is associative. Okay. So by simple calculation, we can see how here we are defining like phi alpha beta of x, like alpha x plus beta. So for, I think this is for commutative I did. It's not for associativity. Okay. So this is for B. Okay. So for B, like we can do for part A also. So here how we are defining phi alpha beta of x, like alpha x plus beta. So first means it is like function means these two are functions only, so it will be have like function only. So phi alpha 1 beta 1. So first we will take phi alpha to beta 2 with x, then we will apply phi alpha 1 beta 1. So after doing this, first we will get alpha to x plus beta 2. After that we will apply phi alpha 1 beta 1. So after doing this, we will get these things. Similarly for this part. So from here means we can see that these two are different. These two are not coming same. So this is not a commutative. And what about associativity? For associativity, we need to just do calculation. If you people do carefully, then we will get this is a commutative. So, but here what in question what they are asking, like they are asking for means like some kind of inverse. For every alpha beta belongs to R square such that alpha is not equal to 0. There exists a AB belongs to R square such that phi alpha beta and phi AB should be equal to phi 1 0. So first what we will do, we will find identity. So to find identity, what we are doing, suppose phi alpha beta star phi AB x, it is coming equal, it should come equal to phi alpha beta of x. This is the definition of identity. So after this we will after this we will simplify this. So what we will get, phi of AB of x is nothing but equal to ax plus b, and this will be equal to alpha x plus beta. So second we will apply this phi on ax plus b, so it will come alpha ax plus b plus beta equal to ax plus b. Like in polynomial, what you do, if we have a two equation like ax plus b equal to cx plus d, so for this we will compare the coefficient of x, coefficient of, like we have polynomials, we will do we will compare coefficient of x and minus 1 like that. So here we have linear. So what we will do, we will compare coefficient of x and then we will compare constant. So here the coefficient of x is alpha a and here the coefficient of x is alpha. So alpha a will be equal to alpha. So from here what we will get, a equal to 1. And if we will compare this constant part, so alpha b plus beta equal to beta. So beta will cancel out. We will get alpha beta equal to 0. So from here we will get beta equal to 0. So hence 1 0 is the identity element. So in question what they are asking, there exists a AB belongs to R2 such that phi alpha b it is commuting with a phi AB should be equal to phi of 1 0. So we will do nothing. Generally we will simplify this. After simplifying this, what we will get, this first product is similar to like this one, what we did here. So it will come like alpha ax plus alpha b plus beta will be equal to x only. Why it is coming x? Because here we have taken 5 1 0 means 1 into x plus 0. So simply we can write x. So again here we will compare coefficient of x and coefficient of constant. So from comparing this coefficient of x, we will get alpha a equal to 1. So from here a equal to 1 by alpha and b equal to minus beta by alpha. Okay. Is it fine to you?
Yes, ma'am.
Is it clear to everyone?
Ma'am, while
Yes, ma'am.
checking associativity,
What?
we,
How to check associativity? 1 minute. Where is
yes,
ha. 1 minute. Okay, start here only. 1 minute. Ha. For associative, what you need to do, suppose you take 3 elements like 3 pairs, alpha 1, beta 1, alpha 2, beta 2, alpha 3, beta 3. So first you want to do phi alpha 1, beta 1, then in bracket phi alpha 2, beta 2 with composition of phi alpha 3, beta 3. So first you simplify it like this. That bracket quantity like this only. After that you apply whatever you get here. Means this quantity you apply like phi alpha 1 beta 1, so you will get some linear equation. Similarly, what you do, first you do like phi alpha 1 beta 1 phi alpha 1 beta 1 star phi alpha 2 beta 2 and star phi alpha 3 beta 3. So first what
ma'am.
you do, huh?
Ma'am, if we take like phi alpha 1 beta 1 composition phi alpha 2 beta 2 first, and then with phi alpha 3 beta 3, then how will this be calculated? I am having trouble.
The thing is, first you like here we don't like suppose we are taking 3. So first what you do, like phi alpha 1 beta 1 composition with phi alpha 2 beta 2 in one bracket, then
Yes,
composition
ma'am.
phi alpha 3 beta 3 over x. So first you do for last term like phi alpha 3 beta 3 of x, what you will get alpha 3x plus beta 3x. Is it clear?
Yes, ma'am.
So after this, what you have like in a bracket phi alpha 1 beta 1 composition phi alpha 2 beta 2, but in the place of x now you have alpha x plus beta. Now what you do is you have to do like this, but here in the place of x now you have to keep alpha 3x plus beta 3x. Is it clear for you?
Yes, ma'am. Clear, ma'am. Clear.
Okay. Okay. What about others?
Can option C be revisited?
What? Option C?
Yes.
Okay.
Ma'am, how to get that value of B?
What? Where?
Ma'am, when we compare the coefficients,
Huh?
we get alpha A equals to 1, right?
Alpha is equal to alpha.
No, alpha A equals to 1. When we compare the coefficients of this
No,
alpha
here,
AX plus alpha B plus beta equals to X.
here we are comparing coefficient of x now.
Yes, ma'am. So we get alpha A equals to 1.
Alpha equal to alpha you will get now. Here in right side what we have, alpha x plus beta. Are you getting?
Okay.
In left hand side, so alpha A will be equal to alpha. So alpha means we can cut that. So we will get A equal to 1.
Okay, so we are proving phi of 1, 0 of X is identity element.
Yeah.
Okay.
Yeah. After this, we will find that inverse when our alpha is not equal to 0. So what about part B? Is it true it will form a group or not?
Yes, ma'am.
What?
No, ma'am. No, it will be not a
Why?
group.
Why?
Because if we take alpha
It
equal
will form a
to
group.
0, then we will not have inverse.
Yeah, correct. So for all real number, like whenever we are taking 0 into A, means 0 cross R. So for those elements, we will not get inverse here. So it will not means it will not form a group. Is it clear to everyone?
Yes, ma'am.
Ma'am, if we take alpha as non-zero, then it will form a group.
So here we have to mention, if in this question, we are saying like alpha beta belongs to R square such that alpha is not equal to 0. So in that case, we can say means this will form a group. But here we are taking whole R cross R.
Yes, ma'am.
Only a few people are responding. What about others? They are getting or not? Okay. So after this, we have another question. I think this one only. Okay, so this question is based on power set. Okay. So this question is asked in CSIR NET 2020 November. So suppose X be a non-empty set and Px is the set of all subset of X. So on Px, we are defining two operations star and delta as follows. Delta is our intersection only, and this it is looking like triangle. This is a symmetric difference. So A union B minus A intersection B. So
Option 3.
option 3. Okay. What about others?
Ma'am, what is symmetric difference?
What?
What is symmetric difference?
Actually, usually sometimes we define like A minus B, then a union of that B minus A, but we can define it like that only. You can see this from Venn diagram.
Okay, ma'am.
Huh.
Option 3, ma'am. Option 3.
Option 3. Okay. Why it will not form under star means intersection? Can you explain?
We don't have identity element.
Okay. We don't have
Ma'am, there is,
identity element. Okay.
ma'am, identity है पर inverse is not there.
So, identity. Okay, so what is the identity here?
Whole set.
Whole set, okay. Correct. What about others? What about symmetric difference like Px is a group under symmetric difference? So what is identity here?
Empty set.
Correct. And what about others? So okay. So here is the remark. Why? P intersection is a semi-group with identities. What do we mean by semi-group? This is like a set G with a binary operation which only satisfy associative property means, and here we have identity element. So we have our So this will form a semi-group, means it will satisfy associative property, and here we have identity X also, because whenever we will take intersection of any subset with X, it will come smaller set only. So we will get same. So here we have identity. And in case of union, it will come here, it will satisfy associativity because A union B union C is equal to A union then B union C. So this will also satisfy associative property. But here our identity is fine. Why? Because whenever we are taking like a union of A union B, so usually we will get that bigger set only. So that's why if we will take union of any set with phi, we will get the same element, same set only. Now, in the case of symmetric difference, so is an abelian group with identity phi and each element has a self-inverse. How we are saying like here means like A minus B. 1 minute. So here how usually we define like A minus B, then A minus B union B minus A, and we can define it like this also. Means in our question it is there A union B minus A intersection B. So here our identity is phi only, because if we will take symmetric difference of A with phi, so A union phi is A only and A intersection phi is phi only. So A minus phi is nothing but A only. So that's why here phi is an identity element. What about inverse? So for inverse, what we need means we want to like A symmetric difference with B should be should come equal to phi. So for that, if we will take A, then A union A is A minus A intersection A. So A minus A is nothing but phi only. So that's why Px is a group, Px will form a group under symmetric difference, and it is abelian also. Is it clear to everyone?
Yes, ma'am.
Yes, yes.
Anyone have doubt, they can ask.
Ma'am, please explain one times in symmetric.
Okay, symmetric difference. So here is the definition. So according to this, what is our means asymmetric difference? B is A union B minus A intersection B. So what we want first, we for a group, what we need associative property, identity inverse. So for associative property, you can check with the help of Venn diagram. It will that is true. The main task is here because you people are not familiar with identity and inverse. So for identity, what we need means what we want a set such that if we will do like suppose E is our identity element. So if you will take symmetric difference of A with E, it should be equal to A. So if you will take A union E minus A intersection E, it should be equal to A only. So if we will take phi, then A union phi will be equal to phi A only. Is it correct?
Yes, ma'am.
And A intersection phi will come phi only. Is it? Are you getting?
Yes, ma'am.
So if you will after that you will minus A union B minus A intersection B, it will be equal to A minus phi. So A minus phi is equal to A only.
Yes, ma'am.
So according to this, your phi will be identity element for symmetric difference. Is it okay to you?
Yes, ma'am.
So identity is clear. Now what we want to find inverse. So for inverse, what we want means suppose we have a set A, we want another set B such that A symmetric difference B should be equal to phi. So for phi, first of all, what we need, if we will take like A union with A same set only, so A union A will be equal to A, and A intersection A will be equal to A. And when we will do like A minus A, it will equal to phi. Is it correct? And this is nothing but this is identity element. So every element is this has its self inverse only. Is it clear to you?
Okay, ma'am.
Is it clear or not?
Yes, ma'am.
Yes, ma'am.
Okay. So now we will move to finite group. A group G is said to be a finite if it has a finitely many elements. Otherwise, we will say G is an infinite group. So mainly here we are talking about cardinality. If cardinality of a set is a finite, then we will say the group is a finite group. If not, then we will say our group is an infinite group. Here are some examples. Okay, so here what I did with Z and F. Here F should be finite. Here F should be our finite field only. Then it will come under the example of finite groups. And these are some examples. We know that cardinality of Z, Q, R, these are means like not finite. These are infinite only, like for Z countable, R, C uncountable. Okay, these are notation how we are denoting this cardinality of G. After this, we have remarked, if F is a finite field and Q with Q elements, then the order of a GLN, means general linear group, will be equal to this. And similarly, what we have order of SLN F, it will equal to Qn minus 1, Qn minus Q till Qn minus 1 by Q minus 1. If F is infinite, then order of these two groups will be infinite. So I think in IIT JAM only they asked one question. Let P be a prime number and let G be a group of 2 cross 2 matrices over ZP with determinant 1 under matrix multiplication. Then the order of group G is. So here what they are saying, they are asking for SL2. Because here we have a collection of all 2 cross 2 matrices such that their determinant is equal to 1. So here they are asking about SL2, where means with field ZP. Here P is the prime, that's why it is filled. So according to this, what should be our answer? Did you get question?
Ma'am, can you show the question once again?
This is the question. Did you get what they are asking?
Yes, yes. People this formula you have,
But P times
you have
P
shown
square
in the
minus one.
previous. Yes, and formula number 2. I think.
Yeah,
What?
we need to use formula number 2 only. So proof of these things we will see in when we will discuss isomorphism theorem and all. For GLN, we can see the proof with the help of matrix, but for SLN, it is little bit tricky to see the proof means normally. So we will see means we can do this proof in the when I will discuss this isomorphism theorem and all. So what will be the answer? Here what we have, our n is equal to 2, and here our field is ZP, means number of element is means cardinality of our field is P. So means our F is a finite field with Q elements. So here we have the field with P elements. So it will come like P square minus 1, then P square minus P, like that only, and like P minus 1. Sorry, here. Correct. P minus 1. So if we will cancel P minus 1, then we will get
P times P square minus 1.
correct. P times P square minus 1. So is it clear to everyone how we will do this type of questions? This is formula based only. Sometimes they may ask. Okay. So after this, this question will, okay, we are defining order of an element. Like we define order of a group, so how we are defining order of an element? The order of an element A in a group G is the smallest positive integer n such that A to the power n equal to E. If no such integer exists, then we say that A has infinite order. Is it clear, this definition?
Yes, ma'am.
So after this, we have a definition of subgroup. Like if G is a group and H is a non-empty subset of G, then we say H is a subgroup of G if H itself is a group under the induced binary operation of G. And for this, we use this notation to mean H is a subset of G. So here is the one simple question: Zn is a subgroup of Z.
No, ma'am.
Why?
No, ma'am. False.
It is not even a subset of Z.
No, we can't say, you can't say like this. Means what means the thing is, what do you mean by Zn?
Means Zn means, ma'am, a set of all integers modulo n.
Correct. So those numbers are coming from Z only. The thing is, here you have different binary operation. For Zn, you have modulo n binary operation. For Z, you have addition as a binary operation. The thing is, these two have different binary operations, so we can't say Zn is a subgroup of Z. Zn means this element is a subset of Z only. And second, we have some tests for subgroup. Let GB is a group and HB is a non-empty set of G, then H is a subgroup of G if only if means closure properties should satisfy. Like if A and B belongs to H, then it should satisfy AB should belongs to H only. And the second thing, if A belongs to H, then it should imply A inverse will be H. After this, we have a second theorem, one-step test. If G is a group and H is a non-empty set, if AB inverse is in H, then we will see H is a subgroup of G. And here is another theorem. If H is a finite set, suppose we have a group, any group, and we are taking any finite set. So in that case, only thing we need to check it is satisfying closure property or not. No need to check inverse things. Okay. After then, we are defining means it is means we can take it as an example of a subgroup of G. Here we are defining like A as all integer power of A. So let G be a group and A belongs to Z. Then A is a subgroup of, means this is subset generated by A. So then this set will form a subgroup of G. Second is center of a G. The center, we denote this by ZG of a group, is the subset of, 1 minute. Is a subset of elements in G that commute with every element of G. That is, means I think these are basic definitions. You people are familiar with this. And after this, what we have, this theorem, center of a group is a subgroup of G. After this, we have centralizer of A in G. Let A be a fixed element of a group G. The centralizer of A in G, C is defined as all those elements of G which is commuting with A. And for each A in a group G, the centralizer of A is a subgroup of G. After this, we have one question. I think it is asked in IIT 2018. So we can tackle what?
And what is the difference between center of a group and centralizer of a group?
It's a centralizer, and the center of group is the, we are taking element which is which is computing with what? Commuting with each element of group. Like suppose if any element A is belonging to Z of G, center of G. So for any element of G, if you will take, then AX will come to X of A. But here we are fixing, if we are taking centralizer of A, so here we are fixing A element. So here we are taking all those element of X which is belonging to G such that A of X equal to X of A. Are you getting?
Ma'am, that is, it means that center of a group is arbitrary and centralizer is fixed.
It's normal for centralizer. We are defining for a single element. So if we are defining centralizer of an element, so it is like centralizer of A. It will come a set of all x belongs to G such that Ax should be equal to x of A. But in case of center of G, here we are taking elements such that which is what to say, means that is commutative with each element. Like here is the definition, no? If we can say like here. So here we are taking all A belongs to G such that Ax equal to x of A for all x belongs to G. But in this case, we are taking G belongs to this group G such that this is commutative with a single element A only. Here we are taking for all. Are you getting?
Yes,
Here
ma'am.
is the difference. Here we are taking for all, but here we are fixing for a single element.
Yeah.
Here we are taking for all x belongs to Z, but here we are fixing it for A only.
Yes.
Center of a group is subset of centralizer of.
Huh. So now we have this problem, question number 28. It asks in IIT exam 2018. So we will tackle this problem with the help of theorem I mentioned. Where it is mentioned here. So here we have two theorems, like means this theorem. So with the help of this, we can tackle this problem. So if we want to check the particular set is a subgroup of G or not, so what we need to check? We need to check it is closed or not. Second thing means for each element of H, its inverse should belongs to H only. So now here, what is this set? So here our group is Z2, means Z2 Z cross Z. Here elements are coming like this in ordered pair. So our first set is all AB belongs to Z2 such that a multiplication of AB is equal to 0. So will you people try this? I'm giving you few minutes. Just try.
I am last option.
Okay, what about others?
Yeah, D is correct, I guess.
Google
Why
D
first? What? Sorry, I
Ma'am, it is
didn't.
not closed under addition, first one.
First one is not true under addition. Okay. What about others? What you people think?
So for ma'am, for one, like one can take A comma 0 or 0 comma B. So we add, then it will be AB. So
yeah.
If like A, B are non-zero, then AB will be A comma B will be non-zero, and A into B will be non-zero. So that is not closed. And for B, for C, let's take like 1 comma 7 and 7 comma 1. So 7 divides 7 and 7 divides 7, yeah. And if you add them up, it will be 8 comma 8, and 7 is not dividing AB.
Yeah, correct.
For B, 0 0 is not there, I guess.
Yeah, correct. 0 0 will
Yeah.
not be here.
So D is correct.
Okay. Okay, so I'm. Okay, so what is there? Let A is equal to ordered pair A1 B1 and B is A2 B2 belongs to H. So A composition B inverse will be equal to A1 B1 plus A minus A2 minus B2. So from here, what we will get A composition B inverse. It will here I am using this first step test only for subgroup. So it will be equal to A1 minus A2 and B1 minus B2. So what we need for for first we want to check whether it is subgroup or not. So for that, what we want to check A composition B inverse should belongs to A. Means that set only. So for that, what is needed? We get this one only, a minus a2 comma b minus b2. So if we want to check, so for that so what is the criteria? A into B should equal to 0. If A comma B is belonging to ordered pair, AB belonging to Z2 something. So here we are taking element AB belongs to Z2 such that A into B is equal to 0. So what we did, we take A equal to A1, A2, B equal to B1, B2. Now what we did, A composition B inverse. Here we are working in addition. So our B inverse will be minus B1 minus B2. So A composition B inverse will be equal to this. So to check it is belonging to H or not, we will take its multiplication. If its multiplication will equal to 0, then we will say it is a subgroup. If it is not coming 0, then we can't say. So for first, what I did, like I have taken this A composition B inverse is equal to A1 A2 comma B1 B2. So A1 minus A2 B1 minus B2, this is equal to A1 B2. Means after simplifying multiplication, I got this. Since A1 B1 and A2 B2, this thing is belonging to H only. So that's why A1 B1 is equal to 0. A2 B2 will be equal to 0. After putting this value, what I am getting minus A1 B2 minus A2 B1. So it need not be equal to 0 in each case. That's why this is not a subgroup. What about part B? In part B, what we are saying, like in part B, we are taking the collection such that 3A plus 2B should be equal to 15. So here, what is our A composition B inverse? This is A1 minus A2, B1 minus B2. So 3A1 minus A2, 3A1 minus A2 plus 2B1 minus B2. This will be equal to 3A1 plus 2B1 minus 3A2 plus 2B2. Both are equal to 15 only. So 15 minus 15 is 0 only. So it is not coming equal to 15. So from here, we can say this is not a group. For third part, what we are it should divide 7. If AB belongs to H, therefore 7 will divide AB, A1 B1, and 7 will divide A2 B2. But AB inverse equal to A1 B1 means this may not divide 7. And someone give example also.
Ma'am, 1001.
Yeah. 1001.
10 and take addition with take sum with 01. So it is not closed. Ma'am, I think in option A you have done some mistakes in calculation.
Okay, in option A.
Yes, ma'am.
A1 B1.
How are you cancelling A1 B1 and A2 B2 in last?
No, I am not cancelling because here A1 B1 is belonging. A1 B1 is my A and A2 B2 is my B.
Okay. So you are using. Okay, you are using the definition.
Yeah. So A1 B1 should be equal to 0, and similarly A2 B2 will be equal to 0 according to definition only.
Yes, ma'am.
So in D, what we have, since A2 is dividing A1 A2 and 3 is dividing B1 B2. So from here, their difference will define 2 and their difference will divide 3. So hence, this is the subgroup. Did you get option number D?
Yes, ma'am.
What about others? Okay. So after this, we have another problem. The problem is, let A is a subset of Z with 0 belonging to A. This question asked in, I think, 2022 or 23 something. 2023. So A is a subset of Z with 0 is belonging to A. For RS belongs to Z, define R of A like R of A for all A belongs to A, and RA plus SA is equal to RA plus SB such that AB belongs to A. So which of the following condition imply that A is a subgroup of the additive group Z? I'm giving you few minutes. Okay, sir, I'm explaining this.
Ma'am, I think
B and C.
A and B.
What?
B and C, I think.
Okay, okay. What about others?
I think D.
Okay. Okay. So now we will see the solution. So what do we mean by A plus A equal to A? A plus A equal to A is nothing but A plus B such that AB belongs to A. So from A plus A equal to A, we can say that means it will satisfy closure property. For all means we are taking A. Suppose we have two elements A and B belongs to A. So if we are taking addition, it is this set is equal to A. It means A plus B is belonging to A only. So from here we can say this is satisfying closure property. Now what we want to check? We want to check whether inverse is belonging to A or not. So suppose we have any element A belongs to A. We want to show that minus A is also belonging to A. So but here we have given that minus 2A is a subset of A. That is minus 2 of X belongs to A for all X belongs to A. Correct? So, but what we have, since X is also belonging to A, minus 2X is also belonging to A. From the condition number A plus A equal to A, minus 2X plus X will be in A only. And this is nothing but equal to minus X only. So from here, we can see that inverse property also. Is it clear? How first is?
Yes, ma'am.
What about others?
Yes, ma'am, clear.
Yes, ma'am.
So now we will go to second. What is the second one? Okay. So here A equal to minus A. So here we have given A equal to minus A. Means no need to check that inverse property. It will be true only. Correct? A equal to minus A means for all A belonging to A, minus A will belong to A only. So for B means automatically inverse properties, it is satisfying inverse property. Now here what is our task? Means we want to check whether it is closed or not. So here what we have given A plus 2A equal to A, that is X plus 2Y belongs to A for all XY belongs to A. Is it okay? Is it okay?
Yes, ma'am.
So now here if we take X equal to 0, so 2Y belongs to A. Is it clear? Similarly, if we we can replace X2 means Y, then we will get 2X belongs to A. So now 2X and Y, these are belonging to A. So if 2X and Y belonging to A, so from the property number this A plus 2A equal to A. So 2X plus 2 into Y will belongs to A. Okay. So from here, what we are implying, like if 2x plus 2y belonging to A, so it should imply x plus y belongs to A. Why? Suppose we are claiming that our x plus y is not belonging to A, then what will happen? If x plus y is not belonging to A, so according to definition, how we define R of A, 2 of x plus y should not belong to 2 of A. But here what we have, 2x plus 2y is belonging to A, but here 2x plus 2y is not belonging to 2A. So it means 2A is not a subset of A. But what we have, A plus 2A is equal to A. So anyway, 2A is a subset of A, but from here we are getting contradiction. So 2x plus 2y belonging to A, it should imply x plus y is belonging to A. Is it clear how B is going?
Yes, ma'am.
Well, 2A is not subset of A. How this is a contradiction?
2A is not a subset of A. Here what we are getting, 2A is not a subset of A, but what we have, A plus 2A is equal to A. Sum of 2, A plus 2A is equal to A. So from here, can you imply that 2A is a subset of A? A plus 2A is equal to A. So how you are defining A plus 2A? If this is x plus 2y. So if you take x equal to 0, so this 2A is nothing but 2A na. So 2A is so 2A will be contained in A only na. But here what we are getting 2A is not a subset of A, but according to the condition, we are means we can claim that 2A is a subset of A. And here we are getting 2A is not a subset of A, so which is a contradiction. Is it clear to you?
Clear, ma'am.
So for option number C, we have given that A equal to minus A and A plus A equal to A. So from A equal to minus A, we can claim it will means that we will get inverse, and from A plus A equal to A, it will satisfy closure property. So from explanation of option A and B, we can directly say C is the true. C is the correct option. So what about option number D? So for option number D, we have counter example. For option number D, the condition is 2A is contained in A and A plus A equal to A. So here we can take A equal to our set A equal to 0, 1, 2. Here 0 is belonging to A. 2A is a subset of A only. 2A is a set of all even positive even integers, which is coming under this A, and A plus A is also equal to A only. But this is not a subgroup of Z because we don't have inverse. Is it clear why D is incorrect?
Yes, ma'am.
Is it clear to everyone?
Yes, ma'am.
Ma'am, one second.
For D, 1 minute. Yeah, your question is for D. For option D, what we have given 2A is contained in A and A plus A equal to A. It is given that, and for A, we have condition A should be subset of Z with 0 belonging to A. So what we did, we take A means like A equal to 0, 1, 2 something. Here 0 is belonging to A. This is a subset, and if you do like 2 of A, it will come set of all positive even integers. So according to this, 2A is a subset of A, correct?
Yes, ma'am.
And A plus A is equal to A only. This is satisfying these two conditions. But still it is not a subgroup of Z because we don't have inverse element. Like inverse of 1 is minus 1, but it is starting from 0.
Yes.
So it is not a subgroup of Z. So option D is incorrect.
Yes, ma'am. Thank you, ma'am.
So now we have this question related to subgroup only. If G is a abelian group, then which of the following is a subgroup of G? So our first set is set of all A belongs to G such that A square equal to E. And second one, A belongs to G such that order of A is less than infinity, means order of A is finite. We are taking all set
All
of
options are correct.
What about others?
Yes, ma'am. All options are correct.
Okay. So here is the explanation. Okay. So if AB belongs to H1, therefore A square equal to B square equal to A. Now AB inverse square will be equal to A square B inverse square. So here we can do interchange, and because these are belonging to H1, so it will be E into E will be equal to E. So this is a subgroup of G. For second option, because here we are taking finite only. So since AB belongs to H2, so order of A is M and order of B equal to M. So now what we can do, order of A equal to M and order of B equal to N is A to the power M will be equal to E, order of B is equal to N. And here we are taking AB to the power Mn means A to the power Mn, B to the power Mn. So here we can rewrite it in this form. So from here what we will get, E to the power N into E to the power N, which is equal to E only. So order of AB is less than equal to Mn only, means order of AB is finite. So this is true only. And similarly we did with the help of two-step test. So first we checked for closure property. Second we are doing for inverse property. So A inverse M is equal to A to the power M inverse, which is equal to E inverse, and inverse of identity element is identity only. And for third option, what we did, this is similar to option number 1 only, because here n is a fixed number only. So in the place of 2 only we need to put n.
Ma'am, number 3 is like a generator of a cyclic group.
What?
Number 3 is like generator of a cyclic group.
What cyclic group?
Generator of a cyclic group.
Means
Number
what
3.
generator? Sorry.
A power n equal to E.
Then?
That is similar to generator of a cyclic group.
Means a generator of a cyclic group, we can, if order of a group is n and A to the power n is equal to E, then only we can say. It's not like every element is not a generator of a cyclic group. Like an element, if their GCD condition is there that is equal to 1, then only we can say a particular element is a generator of a cyclic group, not in each case.
Okay, ma'am.
And here are some properties, like order of A is equal to order of A inverse for all A belongs to G. Second one is order of XA, X inverse will be equal to,
Ma'am, in last example, S3 is a subgroup of S2. This is true.
S3 is a S3.
Subgroup of
Here we are,
S2.
no, here n is a fixed number. Here n is not varying over natural number. So we can't say like this. If you are taking a particular n equal to 2, here you can take n equal to 3 also, n equal to 4 also. So in that case, we can't say like that.
So S3 is a subgroup of S2, no ma'am? Because all the elements of S3 has...
Sorry. I thought you were talking about H3 and H1. These are finite. H3 is a subset of H2 only, because here we are taking all elements which are of finite order only. So H3 will come under H2 only.
Yes, ma'am.
So here are some remarks, like order of AB will be equal to order of BA for all AB belongs to G. Order of A is equal to order of A inverse, and order of X, A X inverse equal to order of A for all X belongs to G. So now we have some examples, like if G is a group, then which of the following is are true? Let G be an abelian group and AB belongs to G, such that order of A is finite and order of B is finite. So what we can say about order of AB? Is it finite, infinite?
Yes, ma'am. It is always finite.
And what about if our G is non-abelian group?
We cannot say it anything.
What about others?
If it is not
In case
abelian,
of
then yeah,
finite,
order can be infinite also.
What if it is a non-abelian then?
It can be infinite, right? Order of AB.
Okay, correct. What about others? Do you have
I
any
think
example for this?
first one is true.
That is
Huh?
yeah.
Second one, maybe true or maybe false.
Okay. Okay, so we will see the proof of first part we did for a question. Why it is coming like this? Okay. So solution of first part is like similar to this problem only. What we did here, like this only. Like part B. Here, this is we have abelian group, and here one thing is there. What I wrote here, AB to the power m of n. We can write it like this if and only if our group is abelian. Here we have given that in question G is abelian. If G was not abelian, then we can't write it like this, because here we means it is given that G is abelian. That's why I wrote here AB to the power mn is equal to A to the power mn, B to the power mn. If our group is non-abelian, then we can't write it and we can't go further. So first one is like this, only this proof. But for second, we have one example. What we took a GL2R, where our A is 0, 1, 1, 0, and our group, our matrix B means second element is 0 to 1 by 2, 0. So here what we have is square of A square is equal to identity and B square is equal to identity. It means order of A and order of B is finite. So now what we will do multiply of A and B. So from here we will get this one. But if we will do like this power n, it will come like this. So it is increasing. We are not getting identity element. It means order of AB is infinite. So in case of non-abelian group, we can't say anything. Is it clear to everyone?
Yes, ma'am.
Yes.
So the second thing, if G is a group such that every what?
Ma'am, your counter example, you have, I think, understand the counter example, but how you choose true and from what you intuitively think about the appearance of this matrix 2 cross 2 be 0, 2 and half 2. Here, if I can see 1 by 3, then it will be order of 3, okay?
Yeah. Means what you want to choose? 3 cross 3 matrix.
No, I'm choosing 0, 3, 1 by 3,
1.
0.
You will get like this only, like 1 by 3 to the power n, 0, 0, 3 to the power n. Hello?
Hello.
Am I audible?
Yes, yes.
So even if you can keep it here like any number k, 0, k, 1 by k, 0, you will get like 1 by k to the power n, 0, 0, k to the power n. So here means 2, 1 by 2, it is means not doing a good role. I just took, you can put any number. Okay, so our next question is, if G is a group such that every element of G is of finite order, then G is a finite. Is it true? What do you think?
No, because it is the group of symmetric difference where
Okay. What about others?
Yes, ma'am.
Okay, so we have example of this power set of natural number with symmetric difference. So here every element has a self-inverse, but this is an infinite group. So this is the question. If G is a finite group of even order, then G has a element of order 2 and number of element of order 2 is odd. Is it true?
yes,
Can you explain me why?
because it is a group of even order and it has a element of order 2 because because I am dividing those element into two groups, which are self inverse and others are not the self inverse. And that's mean I'm forming two group, two part. A one part is A is equal to A inverse and other part is A not equal to A inverse. Then yes, and non-identity and identity also
Yeah, correct. What about others? Are you people getting? How can we tackle this?
Ma'am, if G is a finite group of even order, then after removing identity element, we will left only odd number of elements.
Okay.
So in a group, every element has inverse. So there will be pairs, ma'am. But we have odd number of elements, so one element must be self-inverse.
Yeah, correct. Okay. So here is the solution for this problem. Here what we are doing, like let A belongs to G. So what we can do, we can divide in three cases. First, an element with order 1, second one, because here what we want to find, G has means number of elements of order 2. So order of all those elements with order 2, and second one is all those all those elements whose order is greater than equal to 2 means order of A is greater than 3. So case 1, when order of A is equal to 1, so it is nothing but A equal to E. Second thing is, because we want to find number of elements of 2, so we are not going to do that. First we will check for this. And order of A is greater than 3, so it will imply A is not equal to A inverse. Therefore, number of order greater than 2 is 2k. Why? Because here A is not equal to A inverse. Here A is not equal to A inverse. So whenever A is coming, we will get A inverse, like A inverse, A1, A inverse, then B inverse, C inverse. So we will get this this collection in even number. So now number of element with order not equal to 2 is 2k plus 1. 1 is like order of A is equal to 1 identity element plus element with order greater than 3. Whenever we will take, then it will come in pair. If A is coming, then A inverse is coming, because order of A is equal to order of A inverse. But because order of A is greater than 3, so A is not equal to A inverse. So like that, we will get 2k plus 1, which is an odd number. And here what we have given, the order of group is even. So whenever we will minus even minus odd, we will get odd. So therefore, number of elements of order 2 is odd. So one question, I think there is just a finite group G such that number of element of order 2 is 12. Is it correct?
Not correct.
From above problem, we can see this. It should be always odd only. So this is, I think, last question only. Let G is a group such that G is a unique element A of order n.
Ma'am,
And yeah.
ma'am, number of odd self-inverse elements excluding identity, then it is odd. If we include identity, then it is even.
Means can you ask again?
Ma'am, number of self-inverse elements in a group, even order group, is even when we include identity, and if we exclude identity, then it is odd.
Number of element with means
Self-inverse elements.
self-inverse element. Self-inverse element is like whose order is A square equal to E. So from here, you can directly say it is odd when, it will be even when we are including E, because the thing is the self-inverse A is equal to, it will be even when we will exclude identity element, then it will be odd.
Yes, sir.
So This is the question. If G is a group such that G has a unique element A of order n is greater than 1, then n equal to 2, A will belongs to center of G, A is equal to E, and cardinality of ZG will greater than 1. So this is the question. I'm giving you few minutes, you people try.
Option 2.
Option 2. Okay, what about others?
All are correct.
Okay, so we will see the solution.
2 and 4, ma'am.
Yeah.
2 and 4.
Okay. Okay, so we will see the solution. Okay. So given that G has a unique element of order n, here n is any fixed number. So order of A is equal to n, so it will be equal to order of A inverse equal to n. But by uniqueness, what we have, A should equal to A inverse, so A square will be equal to E. Is it fine? So from here we can claim n will be equal to 2. So option number 1 is correct only. Okay. And second, what we have, order of x inverse Ax equal to order of A for all x belongs to G. So by uniqueness, x inverse Ax equal to A by uniqueness of A for all x belongs to G. So from here we can claim that Ax equal to A, XA, that is A is belonging to Z of G. So from here we can say order of ZG, center of group, is greater than equal to 1 because identity element is always there. Now we get one more element A belonging to Z of G. So from here we can say that order of ZG is greater than 1. So from here all options are correct. Is it clear to everyone how it is happening?
Yes, ma'am.
I think it is clear,
Yep.
but I have to ask two confusion about it is always true that order of A is equal to order of A inverse and order of X inverse Ax is equal to order of A. It is always true for any group.
Yeah. It is true.
And here is it asked that as A elements would be unique here. That is why A for A inverse and X inverse Ax is equal to A. From combining those two cases, we are getting order of the center of group is greater than 1 because it is usually always content identity and those elements.
Yeah.
So,
Okay, so this was the last question of today's session. So anyone have doubt, they can ask me. In next session, I will try to take define unitary group and all and cyclic group.
ma'am,
Yes, sir.
ma'am, I have a problem in the forming of counter example. I think you have today shown two counter example for eliminating those options. And this type of more question, if I can get, then I think on its my own, so that counter example are very helpful in eliminating those options sometimes.
Can you say it
Please.
again, Mr. Please?
Yeah,
ma'am,
he is asking to provide more examples where we can use counter examples to.
Okay.
Yeah,
yes, on
yes.
on our own for homework as it, and after that we are discussing in group.
Okay, we will try to include in the future sessions.
Okay.
Yeah.
Okay.
So thank you, Ekta, for this nice session with a good collection of problems, and you have explained the details very well. And also our participants, I think many of them have really engaged and made the session very active. Thank you, everyone. And now it is your time to share the feedback. Feel free to switch on your video and introduce yourself and share your feedback and comments about the session.
First of all, sir, my camera is not working well because of the problem in the laptop. That is why I am asking, sir. This session are very helpful because all of us here try to interact and making this session very engaging. And I request to please put a session according to your convenience and ma'am also and others, whatever will like to take session on this examination purpose.
Okay, thank you, Supradim Sandra, for your feedback.
Good afternoon.
Yes, Varada.
Good afternoon, ma'am. My name is Varada. I'm an undergrad student from PSJ Krishnamal College, Coimbatore. So I found today's session on group theory very insightful. You actually begin by discussing the basics. So it was like a recap about what all we have already studied. And you also discussed many of the important questions from the JAM point of view. So yeah, overall it was very useful for us and looking forward to the next sessions by you. So thank you so much, ma'am, for providing this wonderful session. And thank you, Vinod sir, for organizing this event.
Thank you so much.
Thank you, Varada.
Hello, ma'am. Ma'am, I'm Archana. Ma'am, I have completed my BSc. I really enjoyed the session. My group theory is not that strong. So when you started, as Varda said, when you started with the basic, it was just reaffirming the foundation of group theory we had. Ma'am, and the more the questions, the better the knowledge. So I really enjoyed the session, ma'am. Thank you, ma'am. Thank you, sir, for arranging the class.
Thank you, Archana. Others?
Hi, ma'am. Hi, sir. I
Yeah.
am Shabita. I really enjoyed the class. My abstract is not much strong, but you revise all such topics from basics. It helped me a lot, and all the questions are new to me. So I got some new ideas from those questions. Thank you so much, ma'am. Thank you, sir.
Yeah, thank you, Shabiba. Yeah, any others?
Hello, ma'am. I am Prakash Pradhan from Laramba College, Laramba. The session was very interesting and the question collection was good. I sometimes I couldn't solve the question, but so thank you, ma'am. Thank you, sir.
Thank you, Prakash. I think from network on his side, his voice is not clear. Yeah, Akash. Yeah.
Good afternoon, ma'am. Ma'am, I think your
Yes.
way of teaching by using questions after explaining concept, then go question. This is a very nice technique for explanation. Thank you, ma'am. I think I will be meet
Thank you.
again in future session.
Thank you, Akash. Yes.
Ma'am, today's program was very much insightful. Thank you for teaching from the basics of group theory and also solving questions alongside. My group theory was not that strong as I'm mathematics. I have mathematics as a past course. Even though I like maths very much. Thank you.
Okay, thank you. Any others?
Good afternoon, ma'am.
Yes.
I'm Guna. Thank you so much for arranging. Thank you so much for the class, and thank you so much for Vinod sir for arranging this class. And it's very helpful. I'm looking forward to the next class.
Okay, thank you, Miduna.
Thank you.
Any others? Alakananta. Any others? If any of you would like to share a feedback, you can do it now. Otherwise, we will wind up the session. Okay, I think some of them, yeah, Ekta, some of them have shared their feedback in the chat box.
Yes, sir.
So anyway, thank you, Ekta, for this nice session. You have taken a lot of effort to prepare the slides and all that. We can share that slides along with the recording of the session. That will
Yes.
be helpful for them. And yeah, hope that we can arrange the next session also according to your convenience. And
Yes.
I know that you are busy with your research and all that. So yeah, anyway, we will arrange it in the nearby time itself.
Yes.
Okay, and thanks to all participants, and I wish all the success to all participants. Also, Ekta, all the very best for your research. Thank you.
Thank you, sir. Thank you, sir, and thank you to everyone for giving this feedback.
Okay, let us wind up here. Bye.
Yes.